In this video, we'll be talking about linear motion sensing. So rather than measuring rotation around an object, here we're measuring distance that's actually moved. And there's a few different ways we can do this. The most simple is probably using a little potentiometer. And rather than a rotational potentiometer that we looked at previously, a linear potentiometer. If you've ever looked at people doing sound mixing and things that DJs do, they have a whole lot of these sliders that can control the volume of each of the instruments or vocals. This is the sort of sensor that we'd use in there. But one of the things with these is they don't tend to move freely. They've got a little bit of resistance to them as you try and push them, and they resist your motion there. And so here, if you use one of these for measuring linear motion, you need to be aware that there is that little bit of resistance in there. And they do wear down over time as well. Another thing we can use is the basic idea that's used within the digital vernier calipers. Essentially within these, they use a capacitive sensing technique where they have two PCBs there and they form what's called a variable or a capacitor that can change in capacitance. And it changes based on the position of our jaws. As we move them further out, we have a different capacitance between those two metal plates and if we move them close together. And the reason this is that capacitors themselves are electronic devices that essentially consist of two metal plates. And based on the surface area of the plates and the relative surface area of the plates that's going to change as that position of the caliper moves, we can infer what distance or how far those jaws are actually open. So as those circuit boards slide over each other, we can count and sense the relative capacitance between those, the variable capacitance is changing, and measure how far we've moved. Now, it's not just something like this. We can get these that we could bolt on, for example, the side of a machine and use it to measure distances of various axes along that machine. And that can give us very fine, down to, well under sub-millimeter accuracy of movements along a linear path. Another way we can do linear displacement measurement is using an LVDT. LVDT stands for Linear Variable Differential Transformer. And these are typically quite expensive, but also super accurate ways of measuring a linear distance. They're essentially composed of a primary coil or a primary winding and then two secondary ones. And then something that can slip in between those that's connected to your output shaft that you're measuring, which is a movable iron core. And that iron core will enable a voltage to be induced into each of those other coils. Now here what we're interested in is in the differential voltage between what's induced into coil 1 and coil 2. Now if that core is right in the middle, dead in the middle of our primary winding, it should be the same in the left secondary coil and the right secondary coil. But if it moves to one side, for example, if it moves to the right secondary coil, that will have a higher induced voltage into that coil that we can measure. And the other one will have a lower induced voltage into it. And so we measure the differential voltage into each of these coils. Now, these are quite expensive. They're used in the industry for all sorts of applications, and they give us an absolute determination of position rather than an incremental one where we're counting how many counts that we've got from a certain position, from maybe a home position. Here, because it's the relative voltage induced into each of these coils, we have an absolute measure. They're quite expensive and used for fairly high value applications. For example, they've been used in accelerated pedals in vehicles to determine how far the accelerator is being depressed.